Hi, this is Andy Yao.
This is Benny Chen.
For our EECE 492 video report, we'll be presenting on wave energy, an investigation into the feasibility of wave energy conversion systems. This is an outline of our video.
I'll be explaining what is wave energy.
And I'll be explaining about energy within waves.
Then we'll discuss the advantages and disadvantages of wave energy. And this will follow by some examples of current applications of wave energy converters.
Following that, the video will take a look at the stance of different countries towards wave energy, leading to a triple bottom line assessment of sustainability for wave energy converters.
The triple bottom line assessment will include the ecological, economic, and social analysis of each system.
The video will then end with a conclusion of our results.
So what is wave energy? Wave energy is a renewable form of energy that is available around the world. The amount of energy that waves produce is estimated to be around 8,000 to 80,000 terawatt-hours globally. So how are waves created? First, wind is caused by the uneven heating of the Earth's surface by the sun. Then, waves occur when friction is created between wind and water particles over the surface of the sea.
Now let us take a closer look at energy within waves. There are two common formulas for wave energy. One for deep waters, where water depth is greater than the wavelength, and one for shallow waters, where water depth is smaller than the wavelength. Here, big P is the wave energy flux per wave, h is significant wave height, small p is the water density, g is gravitational acceleration, t is wave period, and d is the water depth. There are two formulas since as waves approach land, they lose energy due to friction. Therefore, it is more desirable for wave energy converters to be within deep waters. These formulas only show how much energy flux is within waves. How much electricity can be generated will depend on the region, climate, season, and design of each individual wave energy converter. This map here shows the average energy in ocean waves around the world in kilowatts per wave crest length. As you can see, the coast of British Columbia has the highest wave energy resources in the world. Wave energy converters are required to withstand calm and violent weather. They need to be able to deal with physical damage as well as extreme power levels generated from large waves created by storms. Currently, thriving storms are one of the main problems behind wave energy converters. Now let us take a closer look at the advantages and disadvantages of wave energy converters.
Wave energy converters are considerably safe and it does not require to be manually operated.
Disadvantages of wave energy conversion may be the complexity of the systems, so design may be tedious. The systems are also expensive to build. They are extremely dependent on external factors such as weather, climate, region, and the seasons. Also, generated electricity has to be transferred from offshore locations to land. The system itself may also be a navigational hazard.
Now I'm going to introduce some of the current application of wave energy. There's a range of different wave energy devices that have been installed around the world. There are at least 100 separate wave energy conversion technologies in existence. The following is a breakdown of the types of wave energy converter. They are categorized into 5 main types. There is the oscillating water column, point absorber, surge device, attenuator, and the overtopping device. First, we're going to talk about the oscillating water column system. The oscillating water column is partly submerged into the ocean front. It consists of a hollow chamber component with an underwater aperture. Inside the hollow chamber, large volume of compressed air is stored. When waves force water into the chamber, compressed air is squeezed out by the water through the aperture into the turbine of the generator. After that, the water level inside hollow space will be lowered purposely to decrease air pressure, and air will be drawn back through the turbine back into the hollow component. Since the system is bidirectional, the oscillating water column will continuously be generating electricity as long as the operation cycle repeats. There are many advantages to OWC. First, it is the most common, therefore most studied and most understood wave energy converter. Moreover, the electrical and mechanical component is above water and only has one moving part. Therefore, it is easier to implement and maintain. Next is the point absorber. The point absorber consists of a buoy and an energy absorber located at the bottom of the device. When the buoy floats on the surface of water, it will absorb mechanical energy in all directions by following the oscillation motion of the water's ripples. As the buoy shifts vertically under the influence of the sea waves, energy is generated by resisting these movements against the perpendicular surface of the energy absorber. Usually, the energy absorber takes the form of a pump or hydraulic-driven plate. There are two options to the utilization of the energy. First, energy can be converted to electricity, then transmitted to shore, or it can be used to pump water to drive a generator on shore. The search device consists of a hinge flap, a flow line, and an energy converter. Most of the structure is submerged in the sea, while the flow line is buried under the seafloor to connect itself to the power plant on land. While most wave energy converters are designed to absorb the mechanical energy created by the rise and fall motion of the waves, the search device is designed to utilize the horizontal forces of the water waves. As water waves flow against the hinge flap of the machine, energy is collected by the hydraulic hinges. Then the hinges will supply mechanical energy to transmit water into the turbines of the generator via the flow line. Next is the attenuator, also known as the contouring device. The attenuator is a snake-like floating structure that rests in parallel position to the ocean floor. The device consists of hollow cylindrical segments hinged together by hydraulic joints. The hydraulic ramp and the hinges are used to operate generators that are also located in the hinges. As the cylindrical body moves with respect to the rise and fall actions of the ocean waves, the hydraulic joints will be forced into movement, creating mechanical energy. The mechanical energy will then be used to power the generator to produce electricity. Lastly, it is the overtopping device. The overtopping device is a floating structure that has a ramp and curved reflectors on one of the sides, and an opening at the top of the flat surface that leads to the reservoir. Inside the opening, there are multiple low-head turbines, which follow the basic operation principle of the traditional hydroelectric generators on land. The ramp is used to elevate incoming waves onto the top of the machine. After the water is forced up the ramp into the reservoir by curved reflectors, water will travel through the turbine before flowing back into the ocean. With the combination of gravitational energy, electricity is produced as water flows downwards into the turbine to operate the generator.
Now let us take a look into the development of wave energy converters in different countries around the world, in order to gain a deeper understanding of why the technology is growing at its current pace. Notable countries that are developing wave energy converters in Asia are China and Japan. China began research and development since the 1980s with a focus on fixed and floating oscillation devices. They currently have over 650 commercial devices in operation, with exports to other countries. Japan, while having no wave energy resources, has a strong interest in this field. Companies in Japan developed some of the world's first wave energy converters. However, wave energy does not qualify for government assistance in Japan, although development still continues. In Europe, in the United Kingdom, which has high wave energy resources, has a variety of support programs offered by the government for research of wave energy converters. The government even introduced a special bill to address marine environmental development. There are numerous commercial and research wave energy converters in progress there. Other countries, such as Denmark and Germany, both have low wave energy resources. However, they are still interested in this area. As a result, the Denmark government provides one of the best support programs in the world for wave energy, and German companies are acquiring and funding wave energy converter companies from other countries, even though their government does not provide financial aid. Two other European countries worth noting are Ireland and Portugal. Ireland has extremely high wave energy resources, and its government provides financial aid for wave energy research and development. As a result, Ireland contains the world's most ambitious programs for developing wave energy programs. Portugal, known as a pioneer for wave energy, has a government that promotes and supports wave energy. The government has even allocated marine areas specifically for research and demonstration of wave energy converter technology. In North America, the United States established a marine energy program that includes wave energy in 2007. Wave energy is supported by the Department of Energy as well as the U.S. Navy. Stakeholders such as the Environmental Protection Agency, the Fish and Wildlife Service, and the National Park Service all have made progress in coordinating their interests in this area. While there has been no long-term commercial usages for wave energy converters, research and development is rapidly increasing in the U.S. In Canada, although Canada has high wave energy resources, especially off the coast of British Columbia, Canada is not known for its interest in wave energy. There are few companies researching this area, and the government has created a framework for offshore power. However, there is no direct support for wave energy in Canada. This brings us to wave energy and sustainability. As you can see, most wave energy development has been in Europe. There has been little development in this area in Canada, but Canada has high wave energy potential, especially in British Columbia. The sustainability triple bottom line analysis for the ecological, economical, and social feasibility of wave energy converters will determine if such technology will be worthwhile for Canada and British Columbia to invest in.
There are several ecological concerns with wave energy converters. There's the impact on the environment and the impact on animal habitats. The potential impact on the environment includes the movement of the sediment on the seabed, change in local water pressure, change in the direction of water flow, and lastly, the change of scenery. On the other hand, there are also impacts on animal habitats. Firstly, there will definitely be effects on local habitats after physical changes are made to the environment. Moreover, artificial structures might become traps to marine animals as there are potential harmful features in all the wave energy devices. Even though there are no greenhouse emissions to these technologies, local water quality will be degraded by the operation of the device. Lastly, the operation of wave energy device will produce noise, vibrations, and electromagnetic fields to the area. There is little study done on the effects of noise, vibration, and electromagnetic fields to animals, but it is highly possible that these will have a negative impact on the local habitats.
For the social analysis, first consider the government and private corporations. Without government support, there will be no or little development in the area of wave energy. For example, wave energy development stopped in England during the 1980s as soon as the government stopped funding the program. Only with recent funding has the program restarted. Additionally, investors believe that wave energy converters are high-risk technologies, especially as many applications are still in their research stages. In BC Hydro had planned demonstrations in this area, but pulled out citing the other projects made these demonstrations pointless. In general, there is not much incentive for governments and private companies to invest in wave energy in the short term, but long-term investment may be worthwhile. Governments should start implementing policies and regulations to allow for advancement in this area. Next, let's consider the psychological issues behind wave energy. As other renewable energy sources such as solar and wind gets promoted, alternatives may be ignored or shunned. Also, the public may not wish to switch to an alternative after familiarizing themselves with old methods. This results in wave energy not getting the attention it should receive.
Wave energy converters' high capital costs in deployment has led to the reduction of investment in the innovative technology. Since the wave energy is still an immature method of generating electricity, the technology is lacking credibility because of constant failures. With increment in fuel costs and fluctuation of energy prices, wave energy converter becomes the apparent financial alternate to electricity production. It is clear that the capital and the operational cost of wave energy converter is fairly high compared to other forms of energy generations. However, it is hard to predict the standard cost for wave energy converters because the technology depends so heavily on the geographic features of its local area. The initial cost of wave energy generation will be 12 to 16 cents per kilowatt hour. These prices are expected to be reduced to 5 to 7 cents per kilowatt hour as understanding towards technology gets better. The table shows the difference in prices of different energy sources.
And this brings us to the conclusion of our report. Wave energy has potential in the area of renewable energy with low environmental impacts. It is gaining momentum, especially in Europe. However, many methods are still experimental and may not be feasible. Outside factors such as region and climate will also greatly affect results. The research and planning for such situations may be tedious.
Wave energy converters are economically, ecologically, and socially feasible for Canada and British Columbia. However, both the opportunities and risk of wave energy converter systems are high. Without government support and funding, it may be hard for wave energy converters to gain foothold in Canada, but it will certainly be a worthwhile investment. And this concludes our report. Thank you for your time.
And this brings us to the conclusion of our report. Wave energy has potential in the area of renewable energy with low environmental impacts. It is gaining momentum, especially in Europe. However, many methods are still experimental and may not be feasible. Outside factors such as region and climate will also greatly affect results. The research and planning for such situations may be tedious.
Wave energy converters are economically, ecologically, and socially feasible for Canada and British Columbia. However, both the opportunities and risk for wave energy converter systems are high. Without government support and funding, it may be hard for wave energy converters to gain a foothold in Canada, but it will certainly be a worthwhile investment. And this concludes our report. Thank you for your time.